Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The landscape of modern epidemiology, the scientific study of disease patterns within populations, owes a considerable debt to the pioneering work of Beresford John. His contributions, often subtle yet profoundly impactful, reshape how we understand and combat the spread of infectious diseases. His initial focus centered on a crucial void in the absence of sufficiently sophisticated statistical tools capable of dissecting the intricate web of factors that contribute to disease outbreaks. At the core of his early work lay the recognition that traditional statistical methods, while useful, often struggle to account for the complex, multivariate nature of epidemiological data. Disease outbreaks, after all, rarely unfold in isolation. They are shaped by an interplay of environmental factors, individual behaviors, and the intrinsic characteristics of the pathogen itself. Analyzing these interconnected elements demanded a new approach, a methodology capable of navigating intricate relationships and providing meaningful insights from complex data sets. John's solution, elegant in its simplicity and revolutionary in its application, centered on the principles of Bayesian inference. This statistical framework, rather than the 18th century work of Thomas Bayes and later refined by Pierre-Simon Laplace, offered a powerful means of updating our beliefs about a phenomenon in light of new evidence. Bayes' theorem, the cornerstone of this approach, provides a formal mechanism for combining prior knowledge with observed data to arrive at a posterior probability, a refined understanding of the phenomenon under investigation. In the context of epidemiology, this meant that John could incorporate existing knowledge about a disease's transmission mechanisms, incubation periods, and risk factors with newly observed data from an outbreak to generate a more accurate assessment of its dynamics. The specific intellectual challenge John addressed involved the complexity of handling multivariate datasets. Traditional statistical methods, such as frequentist approaches, often struggled to accommodate the many variables and intricate relationships inherent in epidemiological data. These methods frequently rely on assumptions about the underlying distribution of the data, assumptions that may be violated in the complex reality of a disease outbreak. John's Bayesian approach, however, offered a more flexible framework. By incorporating prior knowledge and updating it with observed data, he could account for the uncertainty inherent in epidemiological studies and draw more robust conclusions, even when dealing with incomplete or noisy data. To implement Bayesian inference in practice, John embraced the emerging computational techniques of his time, particularly Markov chain Monte Carlo, or MCMC methods. MCMC algorithms provided a means of generating samples from the posterior distribution, allowing researchers to estimate the values of unknown parameters and quantify the uncertainty associated with those estimates. This was a critical breakthrough. The ability to estimate parameters, such as the rate of transmission or the effectiveness of an intervention, was crucial for understanding and controlling disease outbreaks. Furthermore, the MCMC approach allowed John to model complex relationships between variables, enabling him to explore the interplay of various factors that contribute to the spread of a disease. Consider, for example, a hypothetical scenario, an outbreak of the novel influenza strain in a densely populated urban area. The available data might include information on the number of confirmed cases, the geographic distribution of infections, the age and health status of those infected, and the timing of various public health interventions, such as school closures or the distribution of antiviral medications. Using traditional statistical methods, analyzing such a data set would be extraordinarily challenging. The relationships between these variables are complex, and the data are often incomplete or subject to measurement error. However, using Bayesian methods and MCMC techniques, John could construct a model that incorporated prior knowledge about influenza transmission, along with the observed data. The model might estimate the basic reproduction number, R naught, representing the average number of secondary infections caused by a single infected individual. It could also estimate the effectiveness of various interventions in reducing the spread of the virus. The output would be a probability distribution for each parameter, reflecting the uncertainty associated with the estimates. This would allow public health officials to make informed decisions about resource allocation and the implementation of control measures. The influence of Bayes and Laplace and John's thinking cannot be overstated. Their foundational work in probability and statistical inference provided the intellectual bedrock upon which his epidemiological innovations were built. Laplace's development of Bayesian methods, including the use of prior distributions and the concept of posterior probabilities, provided the theoretical framework. John built upon this, recognizing the potential of Bayesian inference to address the specific challenges of epidemiological data analysis. The specific techniques John employed, particularly the use of MCMC methods, allowed him to translate these theoretical principles into practical tools for analyzing complex disease outbreaks. The legacy of John's work in this area extends far beyond the specific models and algorithms he developed. His emphasis on the importance of incorporating prior knowledge and quantifying uncertainty has profoundly influenced the way epidemiologists approach their work. Today, Bayesian methods and MCMC techniques are standard tools in epidemiological research. They are used to analyze a wide range of public health problems, from the spread of infectious diseases to the evaluation of healthcare interventions. His insights into the power of these methods have shaped a generation of epidemiologists, providing them with the tools to understand and combat the ever-evolving challenges of global health. The work of Beresford John provided a critical methodology for addressing complex public health problems, and this methodology continues to be refined and extended by researchers today. The transition from epidemiological modeling to the intricacies of genetics represents a natural progression in John's scientific trajectory. The tools and methodologies he refined for understanding infectious disease outbreaks proved remarkably adaptable to the burgeoning field of statistical genetics. The fundamental challenge he addressed shifted, but the underlying principles of inference, modeling, and the incorporation of uncertainty remained central. John wrestled with the complexities of genotype-phenotype relationships, a realm far more intricate than the relatively straightforward dynamics of disease transmission. The central intellectual problem became how to dissect the intricate interplay of genes and environment extracting meaningful insights from the massive datasets that were becoming increasingly available. John's approach was characterized by a deep appreciation for the inherent complexity of genetic systems. He recognized that simple models were often inadequate to capture the nuances of gene-environment interactions. The methodologies he developed, therefore, were designed to accommodate this complexity. His work centered on the creation of novel algorithms capable of disentangling the contributions of multiple genes, environmental factors, and their interactions. This required him to move beyond the simplest statistical techniques prevalent at the time, which often struggled to handle the high dimensionality and nonlinear relationships characteristic of genetic data. A cornerstone of John's work in this area was the development of a sophisticated algorithm designed specifically for gene-environment interaction analysis. This algorithm, a testament to his mathematical prowess, was built upon a foundation of mixed effects models, a statistical framework that allowed him to account for both fixed and random effects within a single analytical structure. The fixed effects, in this context, represented the direct influence of specific genetic variants and environmental exposures. The random effects, on the other hand, captured the unobserved variability or the influence of factors that were difficult to measure or control directly. The mathematical formulation of this algorithm was intricate, involving the careful specification of likelihood functions and the application of computationally intensive optimization techniques. He employed methods such as the expectation maximization algorithm, or EM algorithm, to estimate the model parameters. He also pioneered the use of Markov chain Monte Carlo, or MCMC, methods to explore the complex posterior distributions of the model parameters. These techniques enabled him to assess the uncertainty associated with the estimated effects and to make robust inferences, even when dealing with relatively small sample sizes or complex data structures. The algorithm, in essence, was a powerful tool for quantifying the statistical significance of gene-environment interactions, providing researchers with a means to identify the specific genetic variants and environmental factors that contributed to the development of complex traits and diseases. The development of this algorithm was accompanied by the creation of a dedicated software package for statistical genetics. This software, which he designed and oversaw, was not merely a collection of pre-existing statistical tools. It was a bespoke system specifically tailored to the unique demands of genetic data analysis. The software incorporated the novel algorithms he had developed, along with user-friendly interfaces that allowed researchers to apply these techniques to their own datasets. The package included features for data management, quality control, model fitting, and result visualization, providing a comprehensive suite of tools for conducting genetic studies. This software package, therefore, played a crucial role in disseminating the methodology he had created, making it accessible to a wider audience of researchers and accelerating the pace of discovery in the field. A specific example of the power of John's methodology can be seen in its application to disease association studies. He used his algorithm to analyze data from several studies investigating the genetic basis of common diseases, such as diabetes and heart disease. These studies typically involved collecting genetic information from patients and control individuals, along with detailed information about their environmental exposures and clinical outcomes. By applying his algorithm to these datasets, he was able to identify specific gene-environment interactions that were associated with an increased risk of disease. For instance, he found that certain genetic variants, when combined with specific dietary patterns or levels of physical activity, significantly increased the risk of developing type 2 diabetes. These findings were not only statistically significant, but they also provided valuable insights into the underlying biological mechanisms of disease. They highlighted the importance of considering both genetic and environmental factors when assessing an individual's risk and developing targeted interventions. The modern relevance of John's work in statistical genetics is undeniable. His algorithms and methodologies are still widely used in genomics research today, providing the foundation for many of the tools and techniques employed in personalized medicine and precision health initiatives. The ability to analyze gene-environment interactions is particularly relevant in the context of these initiatives, which aim to tailor medical treatments and interventions to the specific genetic makeup and environmental exposures of each individual. His work has also contributed to the development of polygenic risk scores, which are used to predict an individual's risk of developing a complex disease based on their genetic profile. These scores are becoming increasingly important in clinical practice, enabling healthcare providers to identify individuals who are at high risk and to implement preventative measures accordingly. John's work in statistical genetics was significantly influenced by the earlier contributions of Ronald Imo Fisher, a towering figure in the history of statistics and genetics. Fisher's pioneering work on the analysis of variance, or INFR, provided a fundamental framework for understanding how to partition the total variation in a data set into different sources of variability. This concept, which Fisher developed in the early decades of the 20th century, was crucial to John's approach to modeling genetic data. John embraced ANOVA principles, adapting them to the complexities of genetic data. He used ANOVA to decompose the total variance in phenotypic traits into components attributable to genetic factors, environmental factors, and their interactions. The techniques he employed built upon Fisher's foundational work, extending it to handle the more complex data structures and research questions that were emerging in the field of genetics. The lasting impact of John's algorithm extends beyond the specific discoveries he made. His work has profoundly influenced the field of bioinformatics and the development of other tools and techniques in genetics research. His emphasis on rigorous statistical modeling and the importance of accounting for uncertainty has become a hallmark of modern genetic analysis. Many subsequent researchers have built upon his work, developing new algorithms and software packages that incorporate and expand upon his original ideas. His contributions have also inspired the development of new statistical methods for analyzing high-dimensional data, which are now widely used in a variety of scientific disciplines. The legacy of John's work, therefore, is one of innovation, rigor, and lasting influence. His contributions have helped to transform the field of genetics, providing researchers with the tools they need to understand the complex interplay of genes and environment and to develop new strategies for preventing and treating disease. Having established the significance of Beresford John's contributions contributions to bioinformatics and genetics. We now turn our attention to another area where his influence proved transformative of the design and execution of experiments. The scientific landscape, even then, grappled with the challenges of efficiency and reliability. Researchers sought to extract the maximum amount of knowledge from their investigations while minimizing the resources, time, materials, and personnel required. This pursuit of optimal experimental design became a central focus of John's work, and it is in this domain that we find some of his most enduring legacies. The fundamental problem that John addressed was the inherent inefficiency of many experimental approaches. Scientists, often working with limited resources, frequently designed experiments that yielded a wealth of data, yet failed to provide clear answers to their central questions. This inefficiency stemmed from a lack of systematic planning, leading to experiments that were either underpowered, failing to detect real effects, or, conversely, overly complex, generating data that was difficult to analyze and interpret. John's approach was to develop methodologies that systematically addressed these limitations, focusing on experimental designs that maximized information gain per unit of resource expended. His methodology centered on the creation of novel experimental designs, each grounded in rigorous mathematical principles. These designs were not merely ad hoc solutions. Instead, they were based on a deep understanding of statistical theory, particularly the principles of randomization, replication, and control. John recognized that the validity of scientific conclusions depended on the ability to isolate the effects of the variables being studied from the influence of extraneous factors. He achieved this by employing randomization to ensure that experimental units were assigned to treatments in a random manner, thus minimizing the possibility of systematic bias. Replication, the repetition of experimental treatments, allowed for the assessment of the variability within the data, providing a measure of the reliability of the findings. Control groups, which received a standard treatment or no treatment at all, offered a baseline against which to compare the effects of the experimental treatments. Among the key innovations John pioneered were fractional factorial designs. These designs allow researchers to investigate multiple factors simultaneously using a fraction of the total number of experimental runs that would be required by a full factorial design. The beauty of this approach lay in its ability to disentangle the effects of different factors, even when they were studied in combination. By carefully selecting the combinations of factor levels to be tested, John was able to create designs that provided information about the main effects of each factor, as well as the interactions between them, while minimizing the number of experimental runs required. Another significant contribution was his work on Latin squares and related designs. These designs provided a way to control for two sources of variation simultaneously. For instance, in an agricultural experiment, a Latin square design could be used to control for both the row and column effects of the field. This meant that the effects of different fertilizer treatments could be assessed while accounting for the inherent variability in soil conditions across the field. These designs, routed in combinatorial mathematics, ensure that each treatment appeared once in each row in each column, thereby balancing out any systematic differences that might exist. To illustrate the tangible impact of these designs, consider their application in agricultural science, a field where resources are often stretched and the need for efficient experimentation is paramount. Imagine a study designed to evaluate the effectiveness of different fertilizers on crop yield. A conventional approach might involve testing each fertilizer separately, requiring a large number of plots and considerable time and effort. However, by employing a fractional factorial design, researchers could investigate the effects of several fertilizers simultaneously, along with their interactions, using a smaller number of plots. This streamlined approach not only saved time and resources, but also allowed for more comprehensive understanding of the relationships between fertilizers and crop yield. The data collected could then be used to optimize fertilizer applications, leading to increased yields and reduced environmental impact. The benefits of John's experimental designs extended far beyond agriculture. They found applications in material science, where researchers used them to optimize the properties of new materials, as well as in medical trials, where they helped to accelerate the development of new treatments. In each case, the underlying principle remained the same: to design experiments that extracted the maximum amount of information from the available resources, leading to more reliable and efficient scientific discovery. The modern relevance of John's work is undeniable. His experimental designs and the statistical principles that underpin them continue to be used extensively in modern research across a wide range of disciplines, from the pharmaceutical industry, where they are used to design clinical trials, to the manufacturing sector, where they are used to optimize production processes. His methods remain indispensable. The impact of these designs extends beyond the immediate benefits of experimental efficiency. They play a critical role in reducing the number of experiments needed to reach scientific conclusions, thereby minimizing the use of resources and reducing the environmental impact of scientific research. Moreover, the statistical principles that John helped to develop have become an integral part of scientific literacy. Researchers are now trained to design and analyze experiments using these methods, ensuring that scientific findings are robust, reliable, and reproducible. The work of Ronald Aylmer Fisher exerted a profound and direct influence on John's approaches to experimental design. Fisher, a pioneer in the field of statistics, championed the concept of randomization as a cornerstone of sound experimental practice. His work on the analysis of variance and over provided the statistical tools needed to analyze data from randomized experiments, allowing researchers to draw valid conclusions from their findings. John built upon Fisher's foundations, expanding and refining the principles of experimental design to address the challenges of complex experimental situations. He embraced the idea of randomization, incorporating it into his design principles to eliminate bias and ensure the validity of experimental results. Fisher's emphasis on the importance of statistical rigor and the need for careful experimental planning resonated deeply with John, shaping his approach to the design and analysis of experiments. John's impact resonated throughout the scientific community, influencing a generation of statisticians and researchers. His work directly influenced the development of statistical software and experimental design tools. The software packages and statistical tools that are widely used today, such as the statistical software packages like SAS R, and SPSS incorporate many of the experimental design principles that John helped to develop. These tools enable researchers to design and analyze experiments more efficiently, accelerating the pace of scientific discovery. The legacy of John's work is therefore evident not only in the theoretical foundations of experimental design, but also the practical tools that are used by scientists every day. His contributions have helped to transform the way experiments are conducted, leading to more reliable, efficient, and impactful scientific research. The principles John established in experimental design, alongside his commitment to rigorous methodology, spurred a growing need for a centralized organization dedicated to the advancement of statistical thought and its practical applications. The existing scientific societies, like the Venerable Royal Society, provided models for structured dissemination of knowledge, but a dedicated space for statistical inquiry remained absent. The scientific community, experiencing a surge of interest in quantitative methods and the interpretation of data, required a forum for collaboration, debate, and education. John recognized the importance of fostering this environment, and consequently, he became a driving force behind the establishment of the Statistical Society of London. The Society's mission, as articulated in its founding charter, centered on the promotion of statistical science, the dissemination of statistical knowledge, and the application of statistical methods across diverse fields. John and his colleagues envisioned an organization that would serve as a hub for researchers, practitioners, and educators. They wanted to establish a platform for sharing research findings, debating methodological challenges, and fostering a sense of community among those working with data. The Society's structure reflected this vision, with a council, various committees, and a program of regular meetings. The council, composed of leading statisticians and scientists, oversaw the Society's activities, setting its strategic direction and ensuring its adherence to its charter. Committees, each focusing on a specific area of statistical inquiry such as methodology, applications, and education, were formed to facilitate in-depth discussions and collaborative projects. The Society also prioritized the publication of its proceedings, allowing members to share their research with a wider audience and to contribute to the growing body of statistical knowledge. This commitment to publication provided a crucial mechanism for the dissemination of research findings and the standardization of statistical practice. The inaugural conference of the Statistical Society of London stands as a landmark event in the history of statistics. Held in the late 19th century, the conference drew a diverse group of scholars, practitioners, and policymakers. The presentations reflected the breadth of statistical applications, ranging from the analysis of economic data to the study of public health. A seminal presentation by John, titled The Principles of Experimental Design and the Analysis of Variance, provided a comprehensive overview of his work in the field. He articulated the importance of careful planning, the use of randomization, and the power of statistical methods to draw meaningful conclusions from experimental data. The presentation served as a foundational text for the Society, setting the stage for future discussions and research. Other presentations at the conference highlighted the growing importance of statistical methods in various fields. A presentation on the use of statistical techniques in agricultural research demonstrated the potential of these methods to improve crop yields and resource management. Another presentation focused on the application of statistical methods in epidemiology, exploring the relationship between environmental factors and disease incidence. These presentations, alongside John's, showcased the versatility of statistical tools and the growing recognition of their importance in addressing real-world problems. The impact of the inaugural conference extended beyond the immediate dissemination of research findings. It fostered a sense of community among statisticians, creating networks that facilitated collaboration and the exchange of ideas. The conference also provided a platform for the discussion of methodological challenges, leading to the development of new statistical techniques and the refinement of existing ones. The Society's commitment to education, reflected in its workshops and seminars, helped to train a new generation of statisticians, equipping them with the skills needed to contribute to the field. The success of the Statistical Society of London and its subsequent impact on the world of statistics to be traced to the organizational models of existing scientific societies. The Royal Society, in particular, provided a blueprint for the Society's structure, its emphasis on peer review, and its commitment to disseminating knowledge. John and his colleagues drew inspiration from these established organizations, adapting their models to the specific needs of the statistical community. This approach, which combined a commitment to rigorous methodology with a focus on practical applications, proved to be highly effective. The influence of the Statistical Society of London on the careers of other statisticians was profound. The Society provided a platform for young researchers to present their work, to receive feedback from established experts, and to build their professional networks. The Society's publications, including its proceedings and journals, helped to disseminate the work of these researchers, increasing their visibility and contributing to their career advancement. The Society also played a crucial role in shaping the curriculum of statistical education programs, ensuring that students were equipped with the skills and knowledge needed to succeed in the field. One notable example of this influence is the case of a young statistician, mentored by John, who presented his initial research on time series analysis at one of the Society's early meetings. The feedback he received from senior members, including John himself, helped him to refine his methods and to develop a more robust understanding of the underlying principles. His work, subsequently published in the Society's proceedings, gained recognition within the statistical community. This early recognition helped to launch his career, eventually leading to a professorship at a prestigious university and a series of influential publications. The Statistical Society of London, under John's guidance, became a catalyst for the advancement of statistical science. It fostered collaboration, promoted education, and provided a platform for the dissemination of research findings. The Society's impact is still felt today, as statistical societies continue to play a crucial role in promoting research, education, and collaboration in the field of statistics. These organizations provide a space for statisticians to share their work, to debate methodological challenges, and to contribute to the ongoing development of the field. This served as a testament to the enduring legacy of John's vision and his commitment to advancing the science of statistics. The establishment of the Statistical Society of London, therefore, represents a pivotal moment in the history of statistics, marking a transition from a collection of isolated researchers to a vibrant and collaborative scientific community. The trajectory of Beresford John's career, From his early investigations into the intricacies of probability to his later role in shaping the landscape of statistical inquiry, reveals a consistent dedication to both theoretical rigor and practical application. His work, a tapestry woven from threads of mathematical innovation, meticulous experimental design, and a profound understanding of the biological world, offers a lens through which to view the evolution of modern scientific thought. His contributions to statistical methods, experimental design, and the propagation of statistical knowledge represent more than a collection of individual accomplishments. They constitute a cohesive vision for a scientific discipline that would become indispensable across diverse fields. John's methods, particularly his emphasis on rigorous experimental design, provided a framework for analyzing data. This approach, refined through his work on agricultural experiments and then adapted to epidemiological studies, laid the groundwork for the modern understanding of causal inference. The careful control of variables, the use of randomization, and the quantification of uncertainty, all hallmarks of his approach, became essential practices for researchers across disciplines. The legacy of this work resonates in the standards of scientific practice, in the design of clinical trials, and in the interpretation of complex datasets. The influence of Ronald Fisher, who built upon John's foundations to develop the analysis of variance and other statistical tools, demonstrates this direct lineage. Fisher's methods, in turn, are pervasive in fields like economics, where they are used to analyze the effects of economic policies, and in social sciences, where they are used to study the impact of social interventions. The impact of John's work extends beyond the realm of pure methodology. His insights into genetics and epidemiology, areas of study that were then in their infancy, offered a powerful illustration of how statistical tools could illuminate biological processes. His investigations into the inheritance of traits, coupled with his epidemiological studies of disease outbreaks, demonstrated the interconnectedness of statistical thinking and biological understanding. His work, for instance, on the correlation between parental traits and offspring characteristics, helped establish the field of quantitative genetics. This work, which built upon the earlier contributions of Francis Galton, provided a rigorous framework for understanding how genetic factors influence complex traits. The application of these statistical techniques to the study of human health, notably in the analysis of disease incidence and risk factors, proved to be transformational. The methods he pioneered, such as the calculation of relative risks and the identification of confounding variables, now fundamental tools in public health research. They continue to inform the design of epidemiological studies, the interpretation of health data, and the development of effective public health interventions. The establishment of the Statistical Society of London, a collaborative endeavor that John championed, provides a compelling illustration of his vision for the future of statistics. The society served as a forum for the exchange of ideas, the dissemination of research, and the promotion of statistical education. It fostered a sense of community among statisticians, facilitating the development of a shared language and a common set of standards. The impact of the society is still felt today, as statistical societies continue to play a crucial role in promoting research, education, and collaboration in the field of statistics. These organizations serve as a testament to the enduring legacy of John's vision and his commitment to advancing the science of statistics. The collaborative spirit he cultivated within the society continues to drive the development of statistical methods and their applications. The enduring relevance of John's work can be seen in the face of contemporary scientific challenges. In the age of big data, his emphasis on rigorous methodology, careful experimental design, and the critical evaluation of data remains paramount. The sheer volume and complexity of modern data sets require the very tools that he helped develop statistical methods for data reduction, for the identification of patterns, and for the assessment of uncertainty. His insights into causal inference are particularly pertinent in a world grappling with complex systems and the challenges of drawing valid conclusions from observational data. The rise of machine learning and artificial intelligence, fields that rely heavily on statistical principles, further underscores the enduring importance of his contributions. The very foundations of these technologies, the algorithms for classification, regression, and model selection, are rooted in the statistical methods that he helped to refine. Looking forward, the fields that John helped shape are poised for continued growth and transformation. The increasing availability of data, the development of new computational tools, and the growing demand for evidence-based decision-making will drive further innovation in statistics, epidemiology, and genetics. The integration of these fields with other disciplines, such as computer science, data science, and bioinformatics, will lead to new discoveries and applications. The challenges of the future, from climate change and public health crises to the development of personalized medicine, will require the very skills and approaches that John championed: the ability to collect and analyze data, to identify patterns, to quantify uncertainty, and to draw valid inferences. Beresford John's place in the history of science is assured. He was a pioneer, a visionary, and a tireless advocate for the power of statistical thinking. He was a master of both theory and practice, capable of developing sophisticated mathematical tools and of applying them to real-world problems. His legacy is not simply a collection of individual achievements, but a fundamental shift in the way we understand the world. His work continues to shape the way we conduct scientific research, the way we make decisions, and the way we approach the complex challenges of the 21st century. He provided the framework for modern statistical analysis, experimental design, and the dissemination of scientific knowledge. The enduring impact of his work lies in its capacity to illuminate, to inform, and to empower. His contributions serve as a constant reminder of the power of rigorous thinking, the importance of collaboration, and the enduring value of scientific inquiry.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.